So as I said, this is a sort of standard machine learning recipe that will come back particularly tomorrow. The first two bits I will be also play a role now. The searching of the search method is a little bit hidden in what I'm going to talk about now, but so still this is the main or this is a very often applied recipe for doing machine learning. And when we apply some machine learning algorithms on our Schnapsen game, if we want to translate Schnapsen behavior into an intelligent agent that uses machine learning, this is exactly what we have to look into. We have to look at the different features that our agent can have. We have to decide on what kind of model to apply, and that might again have impact on the features. And then the algorithm, what the algorithm itself does is to search, according to the different models that we choose, the right model that fits best our problem. So let's get a little bit into what this means, is sort of feature selection. And tomorrow you will see that this has a big impact on the learning problem itself, as I said. So the data set that will be used here is one that predicts the fact whether someone is a male or female on the basis of the age and height of these people. Yeah? So it's a very simple binary classification where we say if someone is 7 and 1 meter 30, then it's probably a female person. So that is what you, very often, that's the way that data is normally specified. You have an instance that hasn't got a name in this case. It's just the feature of the first instance is that it is 3 years old. Value of the feature age for this instance is 3. And the value of the feature height is 105. And the value of the class that it belongs to is male. And then the machine learning task is that you get this data, such a data set. You train some kind of model on it, classifier. And this classifier should predict on new and unseen data whether some new instance with property, a certain age and with a certain height is more probably is more likely to be a female or a male. The way that this is very often represented is in this graphical way, where the feature space is one dimension in a many-dimensional vector space. And the point being here that in principle, this is a vector representation of this one instance. So if you have one dimension that specifies the age, one dimension that specifies the height, then the vector 9, 132 is a good representation of this one point in the universe that describes this specific person, or what it is in this case. And the colors here give us the class that they belong to. Yeah? So here we basically have 40-year-olds, this line is all the 40-year-olds, and this column is one of all the 40-year-olds, and the rows are the people with the same height. So this is pictures that you will see today more, that you particularly will see tomorrow, because the task now in classification, and that's what we're going to talk about tomorrow in particular, will be to sort of find a function or a line that tells us if to separate a separation between the red dots and the blue dots. And as you can see, this is non-trivial because we have these examples. Where would you draw the line? How would you define a function that does this classification? And of course, this is sort of intrinsic to our problem. There is no easy way of separating male and female people based on the age and their height. But this is exactly the kind of problem that you have to face when you do machine learning. So here, let's look at a regression problem. So we have an example space where we have 2 dimensions. We have a dimension x and a dimension y. And we want to predict the value f of x for a new object x. And we want to do that by defining a function that takes as input one of the features of the objects and gives as output the value of it. So this function that you see here is this image is a different coordinate system than the one we saw before. But the task is similar. Now we want to fit a line to this. Well, we would predict that if we find something here in the middle, that the x should be on top of this one. So one of the possibilities to come up with a model, so we're now looking for different types of models that would be useful in this task. And one of the things that could be useful in this task is to come up with a model that is simply a line. Yeah? It's not really very good because for this example, it would give a rather wrong prediction. So you could also think of a different type of model, namely a curve that you could fit. And that would be better for these. It still would be not very good for this one. Now, this would be an option. So it's a more complex curve. So this is probably just a quadratic curve, and this is a sinusoid. I don't really know what kind of geometric structure that would be. And this is now perfect. Matching all these points that all our training data. All these crosses correspond to one of the training data. But the same would hold for this function. So I've shown you now 5 different functions, or 4. Orange one, red, blue. And the question is, which one is the best function? So do we have a linear function that applies? That would be the line. Quadratic one, that would be the one line with one direction without a change in direction. So this is the first task in the recipe. How do you decide on what kind of model class you want to apply? And tomorrow we will see that most of the current machine learning algorithms work with planes, so simple lines in a more-dimensional space, hyperplane planes. And that the trick to avoid this, the fact that there are some examples that do not fit very well, is taken care by remodeling the features. Here we talk about only the choice of the model, basically the type of function that we want to fit this data to. And what you probably all can see that the orange and the blue one, they have big disadvantages. So the red one is too coarse in this case, probably. The green one is okay, but has this exception. The blue one might also be good, but that depends on the data, so you would have to check for new unseen data. But it's also clear that the orange one will be an overfitting. It will be maybe okay with your data that you have for training, but the chance that you find a new data point that is on this line is relatively small unless you know the perfect function. So this is the problem of overfitting, as it's called. So you want to fit a curve, and if you concentrate fully on fitting your training data, then it will usually not work on the new data that you get. So it's always a balance to find a curve that is simple, which helps you predict new data, usually better than something that's so complicated that it works on all your training data, but it will usually not perform very well on unseen data. So the term of overfitting is one that you really have to be aware of, that you should avoid. So it's not a goal on itself to perform 100% on your training data, because that usually implies that you might have made your model too specific and that it is not capable of dealing with the test data that you have put aside. It will usually not work as well. I don't know what I wanted to say with this slide, but the point is that we usually want to find things things that fit your curve as well as possible, while being as simple as possible and generic as possible. And that is a principle that goes back hundreds of years, and it's usually called the Occam's razor principle, after William von Occam, a monk living in the 14th century, and it really is the principle of parsimony. Try to be as simple as possible, try to make models that are as short as possible, try to make, if you can make a distinction with a line or a plane or a hyperplane, use a more simple model. It usually is the better way of doing it. So one should not increase beyond what is necessary, the number of entities required to explain anything, and that is also applied to the model. One should not have a model that is more complex than what is needed. So that was sort of the generic part, and now I want to be really hands-on, given work on one of the typical classifiers that is used when we do, for example, spam filtering, and the principle is based on Bayes' rule, and it's called naive Bayes, and I will explain why it's called Bayes classification. I will also explain why it's called naive Bayes. Is there anybody in the room who knows this, or is it sort of have you seen this before?
Yeah, we had it in the previous course, but
okay, which course was it topic?
Pervasive.
Okay, so you've all okay, so that's but you've all forgotten.
Yeah.
Good. That's always good to do. So so the task is binary classification. We just want a piece of text, such as you get in an email every day, and you want it to be distinguished. You want to define a model that distinguishes between the ones that you want to read and the ones you don't want to read, so the spam and the ham. And what is the method that we apply? We look at many emails that we have gotten, and you have the spam button on your browser, on your email tool, which classifies which builds basically up your training sets. So that's why it's useful to do this. The more you label your spam, the better your spam filter will work. And basically, the spam filter now collects a data set of spam emails that you have gotten and labeled as such, and emails that you have read and not thrown away. And it's the basis of those that it will make a decision what to do with the next one, the next email that it hasn't seen. And basically what we want to do, the principle that we want to use is the principle of uncertainty, but some kind of probabilistic estimation of, is the text that comes in, is it spam or is it ham, by estimating whether the probability of the email being spam, based on the features of the words that I have recognized before, which of the probabilities is higher, that it is spam or that it is ham. Yeah? So the principle is very simple, and it is basically exactly the sort of the table we started out with. We have a table of features where each of the features is word occurrence, and we just make a decision based on the probability of this email being ham or being spam. On the conditional probability, given these words, is the probability higher that this is spam or that it's ham? And we do this using Bayes' theorem, which basically allows us to define this probability that I've just talked about by the product of the probability that things are spam times the probability that a word occurs in the spam, because that's something that's easy to count given that I have the training data, divided by the occurrence of the words in the first place. So that is sort of weighted by the number of words in all the emails that I get in the first place. And the good thing is that the denominator doesn't depend on the class, so that's independent of whether it is spam or it's not spam. So we use that later to simplify the calculation. The problem with this is, as you've learned from Natalia is that to write down this conditional probability is problematic. If we have many features, you will have, based on the chaining rule, you will have to calculate all the dependencies on all the features from each other. So you will have to calculate a very, very long probability distribution, which makes this in principle infeasible. So, in order to solve this problem, there is the assumption made that the occurrence of words in our example is independent. So all the words have the same probability of occurring, even if there is another word in. And that's obviously not true. So if I have the words New and York, there is a probability that they occur together. I could also have taken an example of the spam domain, but that would be more difficult to come up with something clean. So you very often have words that depend on each other. So this assumption is clearly wrong. But this is the assumption of conditional independence of the feature, so the words that we are taking for our learning process. This is what this makes naive, because this really is naive assumption that the words are independent. Still, this is how it's done, and this is what works astonishingly well. So basically, technically, what's happening is that you assume conditional independence. So basically, the naive assumption is that you can calculate the conditional probability of a feature given some other feature without taking this other feature into account. So you forget about all the other words in your probability estimate, and then you can just multiply all the conditional probabilities together. So basically, instead of writing this complex formula with the product rule, I just have to multiply all the probabilities. And that gives us the naive classifier. So basically, if I want to classify a document with features f1 to fn, then I take the most likely, so the one with the highest probability, where the prior probability of the class is calculated by simply counting from how many of the documents in my collection are spam and how many are ham, and then multiplying it with all the conditional probabilities. And it's naive because this formula is an approximation of the real one, and actually we have also gotten rid of the numerator, because that was independent on the class. So it is the same for both ham and spam. So if you only use this for ranking and classification, then you don't need to calculate the probability of the features because it's the same for both. Yeah? So basically this is all you need. You have the naive assumption, and you have the assumption that you do not have to calculate the proper probabilities for doing the ranking. So you have done it with Natalia, but for the fun of things, let's do it anyway. Let's do a hand-on exercise, because this is something I want you to do in the exam, just for fun. Give me take 3 minutes and think of 5 words that describe the content of, you probably don't have pen or paper, but think of it, 5 words describing the course Intelligent Systems and the course Web Technology, which you should have all followed. Just think of the words that you come up with in your mind. Oh God, this is a year ago. I can't remember anything. And write it down on a piece of paper. Choose one. Sorry, I wasn't precise enough. You have to choose Intelligent Systems, or you have to choose Web Technology. Yeah, choose one, describe it in your words, and we're training to learn which of the things you meant. I should have taken pervasive computing. That would have been a better example. Okay, 3 minutes are over. So, have you turned yourself into either intelligent system or web technology person? Yeah? Okay, good. So we'll take, of course, we do this properly, so we'll have 60% our training set and 40% is our test set. So you'll here, this is going to be the training set, yeah? So we're testing on you later, yeah? And we're training on your side. So what are the features? If you want to do this classification.
Practical sessions? Practical sessions?
That's one feature. So I think the words. If you would have to write something describing web technology for me in half a page, what would be the words that you would use? And each of these words is a feature. So I would think of topics that could be distinguishing between the two. So give me some words describing intelligent systems. Come up with the right ones, please. So what is intelligent system?
Interesting lectures.
Let's keep it on content. Let's not get into sort of, let's just, what it's about. Otherwise we get into troubled water. Schnapsen. And that is probably the one here. Anything else?
Adaptivity.
Adaptivity. Okay. Okay. Any more? Let's do 3 or 4 or 5. Let's do. They are. 2 more. Programming. Okay, people from the web technology world, what you've done. The training people, the testing people are also allowed to contribute features.
REST.
What?
REST.
REST. Not in the sense of having a break, I guess.
No.
Good. Any other web technology things? HTTP, thank you. Okay. We could go on here, but that should probably be good enough for the moment. So now we have to do the sort of the training. We have to do the in base learning. This is by estimating the prior probabilities. So how do we do this? We do this by counting, and we do this by counting on the training set. So now please raise your hand if you have. If you are an intelligent systems person and you have the word Schnapsen on your piece of paper. How many of the web technology people have Schnapsen on their? Also, adaptivity. How many of the intelligent systems people have adaptivity? You don't count on the side. You're the testing. You're the testing people. So 3. AI. Who's got AI from the? Oh yeah. So I'm sorry. I'm completely wrong. So 3 intelligent system. Anybody from the web technology has adaptivity? No. AI, intelligent systems. Yes. That's a lot. Pervasive. No, what is it? Web technology. No. Let's do 1. It's more interesting if we have 1. So it's one of them. Who thought about programming for intelligent systems? 5. Who thought about programming in web technology? 1. Really? Who thought about REST in web technology and AI? You don't count, unfortunately. Who thought about HTTP in
What?
Oh yeah, good point. Yeah, in intelligent systems. Sorry. 0. Who thought about HTTP in web technology? Oh, good. So me being stupid. So that's 15. Okay. So that's the first thing you do. You just look at your collection and you count the words. What else do we have to do next is we have split in training and testing set. We have decided on the features. We have now counted the occurrences. And now we have to calculate we have to maximize the conditional probabilities. So basically we need to calculate the priors for web technology and the priors for intelligent systems. So who of you thought about web technology? That can't be because 15 people thought about web technology in the example. So I say all of you, so let's make it 15 in web technology. So that would be, we'll take 15 people and intelligent systems, all the others. So that is, I don't know, 75. Yeah? Oh no, we are in the training anyway, you believe it. What else do we need? We need the priors for web technology, and those we calculate simply by estimating the number of people who used web technology over web technology plus IS. And we need the conditional probabilities for each of the words. Yeah? So given that someone said web technology, the probability of the word occurring is 1 out of 15. Yeah? So now we have we can fill in this wonderful table of our P of Schnapsen, and the class is web technology or IS, and this would be 0, and the class of, out of these 15, 10 people have thought about Schnapsen. 75. Okay. Here we have 3 out of 75. And 0. Here we have 1 out of 15 and 20 out of 75. Please interrupt me if this is unclear what I do. But if you have had this in web technology, then in pervasive computing, it should be familiar. You should be familiar with this. So you just count the occurrences in your training data. You calculate the prior probabilities of the classes. You calculate the conditional probabilities of the features occurring in the class, and you do that for all your examples. Yeah? And at the end, you have to do what's called smoothing. Again, something you should be aware of, that this number is too small. It will, first of all, it will destroy all your mathematics as it being a 0. But it's all unrealistically small. It's just so small because we have such a small training data. So if we had a huge data set, it would be bigger. So how is this solved? It's solved by what's called smoothing, that you simply add some very small value to it. So that would be a smoothing by adding a value. You could also add one occurrence to it, so there are different ways of doing it. I just suggest to do this one now, where you just say if the value is 0, you give it a very small value instead. And then we can fill the table as we start doing here now. And based on this table, we can now calculate the probability of the class being ham or spam, or in our case, a person talking about web technology or about intelligent systems based on these probability that I have calculated a priori upfront from this part of the room. So basically, if you would give me now your 5 terms that you can come up with, you want to do the other? Yeah? Just make them up now. You may also take some of those. Adaptivity. Yeah, more programming. Yeah. Nobody ever takes logic in this when I do this, so thank you. So this is now the training data that we get, and now the question is he an intelligent system person or is he a web technology person? And how do we calculate that? We have to calculate the probability of this being a web technology guess or this being an intelligent systems guess by just filling in the probability of the prior probability of this as we have learned it before in our training set here. So we know the probability of the prior probability, the conditional probability of ML occurring for IS and so forth. Yeah. So this is something that you have to be familiar with. It's one of the most fundamental, simplest, and also widespread learning method because it's very fast, because of the naive assumption, but it's very effective. So even though we badly violate often this independence assumption, it works often very well. And the reason for that is that classification is to predict the correct label and not to predict the right probability. So we do not calculate any probabilities here because we don't do the weighting with the length of the occurrences of the features. We violate the naive assumption, the independence assumption, so I have a really naive approach. So this is really not about correctly predicting probabilities of an email being spam or not. It is about being more likely than another. And this is very important. So that is this naiveness assumption would in many cases not work, but for this classification task is work because you do the comparison between the chances, the likelihood of two classes occurring, and that one is not violated, or that one works in principle very well. So now coming back to the example of what kind of model should I choose in a machine learning approach for an application. So the example is again, we can sort of represent it again in our two-dimensional space. We have classes with a feature that a certain word machine learning occurs and a certain feature AI occurs. And we have some kind of distinction between the two. And in this case, in Bayes learning, this is not a strict line, as we will see tomorrow in the more modern classification approaches, but it's a continuous decision boundary. So there is a probability distribution that is very high in this part of the feature space, and a probability distribution for the other class that is very high on the other part of the space. And in the middle, the probabilities become more or less the same. So we can't talk about a strict line separating the two classes, but we are talking about more a kind of heat map separation. So we've got 10 minutes left, and now that's probably the most useful and interesting information of today. Thinking about ways of now using the learning classification problems or regression problems in our own games of Schnapsen, and the intuition for this comes from Go, which, as I said in the first weeks, has now really become a huge success by beating a human player for the first time. So now the question is, where is here a place where we can use a machine learning algorithm, a classification model, to help us in our game, to make our agents more clever, and that will be the task of the third week. So the working sheet should be out tonight or tomorrow, And the question is, where can we apply it? Or where is it applied in Go, for example? So remember, we have the min-max approach that works on phase 2 of the Schnapsen game, and that is also what's used in Go. So we have a slightly different situation with Go, and I will start with Go. Yeah. So the nature of Go is that I think it has a 19 by 19 field where you can put in stones. So basically, the branching factor is I think 380 in the beginning, and it gets smaller after some time. That is not as much as we have in Schnapsen, because remember that we have all these belief states where you don't really know what cards the opponent has. So in the breadth of your search tree, Go is easier. What you have in Go, though, is that you have many options you have, and the game is far longer. In Schnapsen, the game is only 10 moves. That's all we have. So the maximum length of our search trees, our game trees, is always 10. So basically what we can do, the big advantage of what we can do is that we can do the random rollouts until we know whether a game has been won or not. So if we just play a random game, 2 bots playing against each other, or one bot simply playing, take a random card and play it, it's very easy. It's just 10 steps long, and I always know whether I win or whether I lose. So the heuristic value in our case is pretty much always known. In Go, on the other hand, you have a tree that is huge with 380 or whatever, 360 branches to choose from, but then it's incredibly deep. So in Go, I have to see what, in Go, what you have to do is that you have to restrict your depth as well. And that makes it interesting in Go to apply 2 different heuristics. Yeah, so I will get to that now. Whereas we in Schnapsen, in principle, only need 1, because the only thing we need to look into is how can we learn to choose from our millions of immediate successes, the belief states, how can we choose the right ones to explore? How do we explore them in the first place? The first thing is that min-max doesn't work for us in Schnapsen because of the breadth of the tree, because we have millions and billions of possible belief states. Min-max also doesn't really work in Go because the breadth is very big and the depth is huge. What they do in Go is to obviously restrict the length, but still. So min-max, as we know, doesn't work for Schnapsen, and it doesn't work for, if we have a phase 1 of Schnapsen, and for Go, it doesn't work either. Still, what people have done is to do this strategy that we also apply in our deep, namely the random rollouts. And that basically means that at a certain time, you decide that you're not calculating the full alphabeta space, the full min-max space, but that you just decide at each of the points a valid move of your opponent, and you play it up to a certain depth. In our case, you play it to the end, because we have only this restricted depth. So in our deep, what you do is you choose a move of you, and then you do randomly sampling some of these rollouts, as they are called. You just play up to the depth at the end of the game, and then you average over how often you win such an average game, and how often you lose. Where our problem is that we need to do the sampling properly because we have so many options. In Go, they have the problem that they need to do the sampling properly, which I will get in a minute, and they have to sort of cut off at the end. And they have then to decide on a position whether it's good or not. So basically what they have to learn in Go is at the end of such a rollout what the value of a position is that they would get to. So if you play AlphaGo, you have to learn at the value of these rollouts that we get for free, they have to learn. So that's place one where AlphaGo learns, which in the first week, I said we do it in a heuristic way, but this turns out to be very difficult. So to decide on the heuristic value of the state of a Go board is very difficult, and that's what they do with the deep neural network. Yeah, so that basically they do some rollouts, and at the end they predict how good this state is. The other thing is that if you do your rollout, you can do it randomly, or you can do it in a more informed way. So basically, why do they go with a rollout here and not over there? And that's what's called the strategy. You can learn a strategy to play. And these is this thing that's far more interesting from our perspective. What do you learn for Schnapsen? And that is the strategy of a game in the first place. What Go does is to implement a very clever, DeepMind does is a clever rollout strategy with a statistical distribution of where do you do the rollouts. And that's called the Monte Carlo tree search algorithm, which I will explain with a bit more time tomorrow morning again. But the basic idea is that you start out with a random choice of your nodes to start with, and then you go down until you get some statistical distributions of a winning or not. And this distribution is moved up to the top of the tree. So this is in the simulation phase. And on the top nodes, there is a distribution measure. So how many rollouts have I done already on one of the nodes in the tree? And according to this distribution, in the next round, the choice is made, which node should I explore further? So in a way, you only explore in these rollouts a particular subpart of the tree, but in a very informed way. And the decision then on which part to do the rollout is again made on some learned examples, on the learned strategy. So that's what they have. They have two different learning algorithms, both based on deep learning. The first one is learning the value of a heuristic at the end of the rollout. The other one is learning the strategy, which to choose. This is the policy network, strategy network, which basically tells me I have to explore this area of the game first, and the value network tells me how good is a certain situation. And we in Schnapsen will only have to look at one of them, named the policy network, left or right, or which of the thousands of nodes that we have, or 100,000 of nodes, do we have to choose in our rollout. We can use that now again in two different ways. We can say we have a simple hill climbing bot, and this hill climbing bot, all it does is to look at the states and say, these are the 5 states that I can reach with my 5 cards that I play, and I just have the learning algorithm to predict which of them is the best of the 5. So that's the strategy learning, the policy learning that you can apply. And basically, on the basis of this, you make the decision how your bot moves. So it's a random bot, which is sort of the same as a random bot. It just chooses one, but now not on a random strategy, but on a learned strategy. Yeah? The second way we can apply the learning is on the rollouts, because RDeep, if you remember correctly, just chooses randomly some samples, and it averages over those. And now instead of choosing randomly, we can also make informed choices where we've learned which of the things to use for our rollout. So these are already 2 strategies that we can apply for integrating a learning algorithm into our Schnapsen bots. So try this at home. Think of features in Schnapsen. This is going to be the sort of first step that we need to take care of for the working sheet and for the learning of our bots. What are the features? And there are the obvious ones, namely, I have card Ace of Heart in my deck, and so forth. So then you have to build this situation, this state. You have to translate the state into a feature set, and train your policy on this one. So the question is, how can we do this policy learning? How can we do this rollouts with the policy function? And how can we maybe do this, also this Monte Carlo tree search that I showed you briefly and that I will show in a little bit more detail tomorrow, I guess. Thank you very much.